So as a reminder, we have our first exam 2 weeks from today. And I am planning on giving the exam on Moodle. And you'll have the whole week to take it. And then on the day that the exam is scheduled on, which is 2 Mondays from now, I'll hold an optional review session for anyone who wants to come and get a review. Okay? Yes?
So we're doing our exam online, and then if you have questions, we just appear on the regular lecture.
Yes. Yep. Exactly. I also have quiz 3 is online, and that's due on Friday at midnight. So make sure you take quiz 3 this week. Okay, now I got a few questions about quiz 2, and I had a request to go over that, so I'll go ahead and run through those questions here at the beginning. So question 1 was, consider the following System Verilog module. What is not a problem with this module? This was admittedly a little confusing. There are 6 options here. So if you're looking for a statement in here that does not represent a problem or a bug. So the A says C is double driven, and it turns out that is actually a problem here because C is driven by this assign statement as well as by this always block. And remember that an assign statement, a continuous assignment statement, and an output from an always block are both drivers, right? They're both associated with a blob of synthesized logic. So C is actually double driven here. That's no good. B says no sensitivity list in the always statement. That's true. There is no sensitivity list given, but whenever you have an always underscore comb, you don't need to provide a sensitivity list because the sensitivity list is any signal that appears inside the always block that's treated as an input, which is a little vague, but treated as an input means that you have it in an expression. That it could be a conditional expression, it could be a case statement expression, or it could be a Boolean expression or an arithmetic expression. But any signal you use in there is going to be an input, and thus will be implied to be in the sensitivity list. So if you change anything that's written as an input, it's going to trigger that always block. Likewise, anything that's assigned inside the always block is treated as an output. So because we assign C in here, both the always block and the assign statement are drivers of C. Yes?
So no sensitivity list is not the issue here, right?
No, that's not.
The answer is B.
That's one of the answers. It's not the only one, as it turns out. I think there was a bug in this one. It was meant to have multiple correct answers. But if you go back and you look, I had to make a change earlier today, and I did a regrade. So if you got that one wrong, it might be okay now. You can go back and check. Okay, so B is not a problem. It's fine. C says cannot use an if statement in System Verilog. You can't use an if statement unless it's part of an always block, right? So that's actually okay. If you had tried to use an if statement outside of an always block, just inside of a module without being in an always block, then you can't use it. So C is not a problem. So if you answered B or C, that should be correct. D says use of a blocking assignment in an always statement. Well, a blocking assignment is just a single equal sign, and yeah, that's fine. That's not a problem. You can do that. You can use a blocking or a non-blocking assignment statement in an always. If you're doing combinational logic, which is what this is, you should use a blocking assignment statement. E is cannot combine always comb and assign statement in one module. Sure, that's not a problem. Not a problem. So that would be, if you answered E, that should be correct as well. And F, the always block has no default assignment for C. When I say C, I'm talking about signal C. And that is a problem. So in this always block, if B is false, then it could be potentially triggered without assigning C.
And we have a latch.
And then you'd have a latch. Now, this is weird. This is one of the things that's confusing, and there's inconsistent behavior. If you run this code through ModelSim, it'll compile and it'll run, right? If you run it through Quartus, you'll get an error. It'll say, you can't put a latch inside an always comb, right? So why does Quartus give you an error and ModelSim doesn't for the same code? Unclear. I think it might have to do with the dialect of Verilog, so there might be a way actually in ModelSim that you could change a setting and make it give you an error for this. I don't know. I never looked into it. But the point is that under default behavior, this will actually go through ModelSim, and it really shouldn't, because the whole point of using always comb is to have the compiler check and make sure you don't have a latch. Okay, so bottom line here is if you answered B, C, D, or E, that you should get credit for that. So this was obviously a very easy problem. Okay, question 2 gives you a module and asks how many input signals are specified. This is also a very easy question. You just have to count. There's 1, 2, 3, 4, 5. There's just counting how many inputs. Oh, those are inputs and outputs. Sorry, yeah, sorry. Val is actually an output, so there would be one less than that, right? So 1, 2, 3, 4. Yeah, thank you. Yeah, not as easy as I thought, I guess. Okay, next question. Consider the following Verilog module. Assume the module is reset with a reset pulse at the start of execution. What is the value of state in the first 3 clock cycles after the reset pulse? It's very important that you understand this kind of sequential behavior, because your CPUs will be using this kind of behavior in establishing data paths when you execute instructions. So the reset, so when you reset it, the value of state will go to 1, 0, 0. But then after you drop reset and you hit the next positive edge of the clock, with reset being low, rising edge, you're going to change state. Now the tricky part here is you have to keep in mind that these are non-blocking assignments, which means that whenever you reference state on the right-hand side of the assignment, that's going to be referring to the old state from the last clock cycle, right? And the order of these statements don't matter, right? So there's no data dependencies in here, right? So the way you have to work this out is whenever you look at the next state, you have to look back at what state was in the previous cycle. So we start out at 1, 0, 0, then in the next cycle, state 2 is going to be 0. State 1 is going to be the old state 2. So the old state, now remember, state 2 is going to be the most significant, so the leftmost bit. So state 1 is going to get 1. And then state 0 is the old state 1 or the old state 0. So 0 or 0 is 0, right? So the next state is 0, 1, 0, right? And then in the third cycle, again, state 2, the first bit, I'm starting with the most significant bit, so state 2 is 0, it's always 0. State 1 is going to be the most significant bit from the last cycle, which is 0, right? And then state 0 is the OR of these 2 bits, right? So that's be 1, so 0, 0, 1. Yes?
In such equations, when you say the following in the cycles after reset, you include the reset cycles, or you say reset the point and starting from reset?
Yeah, it's a little vague, but what I meant was you're including the reset, whatever the reset value is, right? So the idea is that you pulse reset, and then you start tracking it after that. Okay. And that's how all these questions will be. I'm not going to try to confuse you with like cycle 0 versus cycle 1, right? Just include the reset state at the beginning. Okay, so question 4 was very similar to the last one. Give the value of signal A in the first 3 clock cycles after reset. So again, when we reset, we get this, if reset A gets 1, 0, 1. So 1, 0, 1. In the next cycle, Now this one's a little strange because we're mixing together blocking and non-blocking assignments. So in this case, we do have a data dependency. We change A, and then the next line of code will recognize the new A, right? So A gets shifted 1 bit to the left, and then it basically, we take the value after shifting it to the left and flip all the bits by doing an XOR with 111. So this value gets shifted. So 101 gets shifted to become 010, so that most significant one goes away. You shift into 0 on the right-hand side, and then 1010 gets flipped to 101. That's what happens when you XOR with ones. And then in the next cycle, you take 101, shift it 1 bit to the left to get 010, and then flip it again, and it once again becomes 101. Right? In fact, it will always be 101. Yes?
In this case, it doesn't matter blocking or non-blocking assignment we have for the second line because there is no anything after that.
That's right, yes. Yeah, the only problem with that is you have to be careful because it doesn't affect anything in here. But if you have another always statement that uses A as an input, it can affect that. So you have to be careful with that. It's best to try to stick to the convention. In this case, though, I did something strange just to make sure you understood the blocking versus non-blocking. But I wouldn't recommend writing code like that. Okay, what is the problem with the following code? A equals A plus 1. Okay, so this is something very common. We're just incrementing a variable, right? This shouldn't be a problem, right? But it is a problem because this is a combinational logic, and we have A as both an input and an output. So if we had done this as a clocked logic, always underscore FF, be fine. It would just literally just be a counter. Every cycle would tick up by 1. But because it's combinational logic, this is going to create a combinatorial or combinational loop, right? It's not synchronized on the clock, so there's nothing to synchronize, there's nothing to control the value of A. So if you run this in model sim will just lock up. It'll just hang because it'll be an endless sequence of triggerings of the always, and it will never converge on a state, right? So the options here were always statement should be combinational but has a cycle, so that's the right answer. Missing sensitivity list, that's not a problem. Cannot use addition in an always com statement. You can do that, it's fine. And use of a blocking assignment, that's fine too. In fact, you're supposed to use blocking assignments with combinational assignment statements. Okay. Number 6, consider the following test bench. What function does some module perform? So for this, we have a self-checking test bench, and you have to infer what the DUT is doing based on what we're expecting, what we're putting in, and what we're expecting out. So I think the easiest way to solve this is to just build a truth table. And so the first row of the truth table is going to be A and B are 1, 1. Okay, then we have a delay, and then we check the output the corresponding output should be a 1. And now this is a little weird. Notice we change A to 0, but we don't specify a B. Well, that's because we want B to stay what it was. Oh, that should just be A and B, by the way. There's no C in there. Sorry, was that what you were going to ask? Sorry about that. There we go. Sorry, it should just be A, B. Yeah, so we didn't specify a B, but we changed A to 0, so B stays 1. And our corresponding expected value for that is 0. And then we change B to 0 without changing A. So again, we leave A as 0, change B to 0. Corresponding output is 0 right there. And then we change A to 1 without changing B, so A becomes 1. And our corresponding output there is a 0. So once we have the truth table, this truth table is the set of test vectors. And just looking at those test vectors, we can see that it looks like that should be an AND gate, right? Just based on the truth table. AND gate, yeah, OR gate. It's not an OR gate because if it was an OR gate, these two rows would be expecting 1. And it's not an XOR gate because then these two would be 1 and that one would be 0. And inverter doesn't make any sense. There's two inputs. Yes?
When you say like none of the above, are you referring to like all of the above?
I'm sorry?
When you say like, none of the above, are you referring to like all of them are not true?
Yes, yeah, sorry. Yeah, you're right. That's a good point. It should, none of the above should be the last option, but Moodle scrambles them. Yeah, Moodle randomized. When I wrote it as the last option, but then Moodle mixes them up. Sorry, yes, that's a good point. Hadn't thought of that. Okay, what are the first three values of A generated from the snippet below? So here's yet another sequential logic. This one is a little trickier though because this one combines the sequential logic with the bit twiddling. So for this one I just put a table together and we have A4 down to 0. So we initialize at 1, 0, 1, 0, 1. Okay, and then in cycle 1 we take A0, that would be this guy, and then 2A1, so A0 and 2A, cycle 1, right. A0 is a 1, and then 2A1, 0, 0, and then not A3, which would be, that's A3, that's 1, and then A2 XOR A4, so that would be a 1 XOR 1 is 0. And then cycle 2, we have, and again, you're looking at the next row up, right, when you figure this out. So A0 is a 0, then we have 2A1, so 1, 1, and then not A3, which would be not 0 is 1, and then A2 XOR A4, so 1 XOR 0 is 1, yeah. Okay. The other thing that's confusing about this is that the bit ordering is implied by this, curly brace operator. So, in this case, you have to look at this and say, well, that, the total number of bits on the right-hand side here is 1, 2, 3, 4, 5, 5, right? So that works out. There's 5 bits, and then the first on the left we have is bit 5, right? And the right is over here would be bit 0. Okay, does that make sense? Okay. Okay, that's it. That was the quiz. The next quiz just has 5 questions on it. And it'll cover the the RISC-V microarchitecture. Okay, so last week I talked about registers. So registers, when you have a register specified like this is like a multi-bit flip-flop for your design. And basically it delays a value from one cycle to the next. It holds a value temporarily. Of course, you can add an enable if you want to hold the value across multiple cycles. And then there are memory arrays, or RAM. I just call them RAMs. The book calls them memory arrays. But a RAM is it's kind of like a register, except the difference is that there's an address that comes in. Now the thing you have to remember about RAMs, the thing that is kind of inconvenient about RAMs is that you can't reset them. You can't just set a whole RAM to 0. Generally that's impossible. If you want to set a RAM to 0, you have to literally walk through every address and set it to 0. Right? So in this case it would take 1,024 cycles to set everything to 0. Generally speaking, RAMs will come up in a random state. Registers, you can have a reset, right? You can have a reset but not a RAM. So RAMs have an address. There's usually one address per port. So in this case, I have one address, means I have one port. I can access one entry in this RAM at a time. But you can build a RAM with multiple ports. In general, though, it's not practical to do that. Usually, the most number of ports you'll see on a RAM is usually 2, with the only exception being the register file, which has 3 ports on it. But register files are always, even on modern day processors, register files are really tiny. Even the most state-of-the-art Intel CPU on the market still has 16 registers on it. So very small. Because registers, I don't know this for sure, but I always thought that register files are literally just sets of registers with a mux at the end. Like it's not even a RAM. Right? We design it as a RAM here, but in practice I think it's literally just a 2D array of flip-flops. because actual RAM arrays that use the little classic six transistor RAM cell, SRAM cell, those are generally limited to 2 ports. Okay, anyway, so yeah, whenever you talk about a RAM, you generally will give the number of entries, which is the number of rows, the number of addresses, and then by the width. So depth by width. Okay, just like in C, just like in linear algebra, but not like in Verilog. In Verilog, when you declare a RAM, you swap. Unclear why. That's horrible, but that's the way they have the language syntax set up. Okay. Okay, and then I gave you some examples here. Now, on an FPGA, you can have this initial statement that you can use to initialize a RAM. Now, you said, I thought you just said you can't reset a RAM. I mean, if you initialize a RAM to 0, isn't it the same as resetting it? Yes, but it's not, because what happens here is that when you configure the FPGA, the RAM gets initialized during the configuration process, right? But once it's configured, you can't globally reset the RAM. Yes?
But maybe you can have a flag initiating that forget whatever is in the RAM, it's a 0 and just skip the read line and had your RAM initialized to 0.
Yeah, you can use like a bypass like we do with the register file. Yeah, that's a good point. In fact, that's a good segue to talk about the register file. So we have the register file code. We're going to give you this. You can use this code for your CPU. And this is the classic register. This is the same register file you learned about when you took 212. The RISC register file is no different at all than the MIPS register file. So there's 3 ports, 2 read ports, 1 write port. Write port is synchronous, meaning it takes a cycle to write. Always takes 1 cycle if you're going to write. But reads are asynchronous. They happen right away. You put an address in, and then the corresponding values of those registers pop out after some propagation delay, combinational propagation delay through the register file. The problem with that is that if it takes 1 cycle to write, but it takes 0 cycles to read, then what happens if you write and read the same value, the same register? Now you've got a problem, because what'll end up happening without you putting some special logic in here, what'll happen is if you write and read the same register, it'll read the old value of the register. You won't be getting the updated. So I'm going to say I'll write to register 2, read from register 2. The value I read will be the old value. So I'll be getting the old value while I'm writing the new value, which could be okay if the rest of your CPU was designed to deal with that. But in the case of our CPU, we're going to use this thing called a bypass, which means that we have this special logic in here with these read ports where if the read address equals the write address, and we're writing, you have to be writing, so write enable has to be that's important. Then we're going to just pass the write data. We're basically going to take whatever is coming in on the write data, and we're just going to forward it directly to the read data, just essentially bypassing the RAM array. So while the RAM array is sitting there trying to write, we're just going to bypass the read logic and just forward the value being written directly out. And that could happen on one or both. Like you can write to register 2 and then read from register 2 on both read ports, in which case the value coming in on write data will be broadcast out to both, right? And that's happening with these 2 guys. And then likewise, if you read from register 0, you'll just get the 0 out, right? Now this is a little strange. You might think, oh, wait a minute, hold on. You bypass register 0, but technically you can still write registers. There's nothing that prevents you from writing register 0 in this always block down here, the write port. And that's true. You can actually write to register 0, but you can never read the value that you wrote, because you get prevented from doing that by this logic. Over the years, we normally have you guys design the register file. But recently, I think starting with last semester, we just gave it out because it wasn't interesting enough to build a whole lab just around the register file. But students in the past would handle this different ways. Some students would initialize register 0 to 0 using an initial block, and then they would not allow the user to write to register 0, right? and then they wouldn't need to put in logic in the read, right? They would just say if the write, like down here, they'd say if the write address is 0, then don't write it, right? But that's an option. I don't know which way is best, to be honest. Yes.
But what's the point in not using register 0 if you have it?
Yeah, I used to wonder about that too. The register 0 allows you to basically do a load immediate, right? Where instead of having an explicit load immediate instruction, you can add a value to register 0, for instance, do an add immediate, right? That's the way MIPS and RISC, that's how MIPS and RISC-V handle it. I think ARM allows you to write to register 0. Now you might say, wait a second, why not just implement a load immediate instruction? Like, right, Intel's got that, IBM has that. There's a lot of architectures that actually have a real load immediate instruction. Why you got to fake it with register 0? Is it that expensive to build a load immediate instruction? Like a hardware load immediate instruction? No, I don't know why they do it that way. It does seem kind of like a bad decision because you basically waste a register. When you could, in fact, and the irony is that the load upper immediate instruction is something that is implemented as hardware, right? So you got to pay for that logic anyway. So I don't know. I don't get it. It's a weird. I think it's a historical. I think they made the decision when they developed MIPS, and then RISC-V is a slight turn on MIPS. So I think it inherited that from MIPS. I think it might be the only architecture that actually has that. Maybe DEC Alpha has that, or Spark or something, but yeah, it's not universal. Let me put it that way. Okay, and then the ALU, we give you the ALU. We've always given out the ALU, but this is your table of ALU opcodes. You're going to have to refer to this when you design your control unit, so just keep that in mind. Essentially, there's one ALU operation for every R-type instruction. Add, subtract, multiply high, multiply unsigned, the shifts, and the compares. And there's the ALU code. There's not much to say about this. It's really just an if then else block. It's all combinational logic, no clock. Pretty simple. Now you might ask, wait a second, how is this add implemented? Is that a carry ripple carry adder? Is that a carry look ahead adder? Is that a carry save adder? How's that synthesized in hardware? I mean, add is something that people build different types of adders. Right? Same thing with multipliers, right? There's a gazillion ways to design a multiplier, right? Which one's being used here? Unclear. I don't know how it decides that. But I'll tell you this. I used to have an example where in my lecture, I used to actually build, in one of my examples, I built a ripple carry adder, and then we synthesize it on the board, and it works, right? In fact, I think I did that earlier. I did that as the demo in this class, actually. But then I replaced it with just using add. Replaced the whole ripple carry, all the full adders and the carry chain, just ripped all that out and just replaced it with a multi-bit add operator, and we synthesized that, and this was like, the clock speed was like 4 times higher, right? So whatever Verilog does when it does this add on the FPGA, when it deploys this add on the FPGA, is much better than a ripple carry. And I think what it does is it uses an FPGA primitive, because the FPGA lookup tables actually have dedicated carry chains that run through the hardware. And as a regular Verilog programmer, you don't get access to those. But if you put add in there, then it will use them. At least I don't think you can access those using, I don't think there's any way to map the carry chain bits coming in and out of the LUTs, unless you use one of their hardware macros, one of their primitive blocks. So anyway, the point is that add, now with multiply, it might be using the hardware multipliers, but there's ways that you could tell it not to. I think there's a pragma you can use to tell it not to, but anyway, that's outside the scope of the course. Okay, so lab 3, we have 22 RISC-V instructions. I mentioned we've got 3 instruction formats that these cover, but there's only one instruction in the U type, that's the LUI. Unlike MIPS that had a 16-bit immediate, in RISC-V we have 12-bit immediates in one type and 20-bit immediates in another, which it adds up to 32, but it's not half-half anymore like it used to be. We also have this crazy func3 field that seems odd, especially considering that we've also got an opcode and a func7. I don't really have a good sense of why those exist, to be honest. I'm sure there's a reason, like where they say, like remember with MIPS, you guys probably remember from MIPS that if the opcode were all zeros, that was a special flag that said, oh, I'm doing an R-type instruction, so look at the function code, right? But that is not true in RISC-V. In RISC-V, there's no obvious rhyme or reason. There's no, like, all the comparison instructions have the same func3 field. I haven't found any patterns like that, so I don't know. Basically, you have to use all three. I'm sure there's some kind of pattern, but I haven't deciphered it yet. Let's see, what else is there to say about this? We've got two source register. Destination register, always in the same spot though. This is nice. You don't need a mux for that anymore. Remember with MIPS, it's like, well, the destination can be here or it could be here, and now it's in one spot. Okay, one thing I want to point out. I had a bug in these slides last week. There's one instruction here called CSRRW. And last week I had this in the R type, but it's actually an I type instruction, and I'm going to talk about that instruction right now. So this stands for Control and Status Register Read and Write. This is an I/O instruction. You guys have never seen an I/O instruction before. That was something that MIPS, I don't think MIPS had any I/O instructions. It had actually, well, there was move to and move from coprocessor instructions, so I guess it kind of did. But anyway, this is an I/O instruction. We're going to use this in this course to have your CPU communicate with peripherals, namely the switches and the 7-segment displays. So the way this works is it's an I-type instruction, and the CSR register is it's in the 12-bit immediate. So you actually have 4,096 potential I/O registers. I don't know how many of them are used. In this class, we're just going to use 2 of them. One for switches, one for the hex displays. So the way this is supposed to work is you read the CSR register, this is the control register, or status register, and you put it into the destination register. And at the same time, you take what's in the RS register and you put it into that CSR register. So you do a swap. You do basically an atomic swap, right? Meaning that you exchange data, or I should say an atomic exchange rather. You exchange data. You take the old CSR, and then you update that CSR at the same time. Okay. Now you might say, well, why would, I don't understand how that doesn't make sense. Like, are we reading the hexes and then writing the hexes, and then are we reading the switches and then writing the switches? And how do you write switches? Because there's no actuators, right? They can't move by themselves. Yeah, so what we're going to do in this class is whenever you want to write the state of the switches, in other words, read the input from the user, which is the switch configuration, into register RD, this is another example where we'll use register 0, right? So I forgot about this, another use of register 0. So we're going to take, the CSR register is 0 for the switches. You guys with me? This is explained in the lab sheet too. But so we're going to associate a special register called CSR register 0. That's going to be our switches. And so whenever we want to read the switches, we'll just specify RD, which is whatever register you want to put the switch value in. It's up to you. But then in terms of sending a value to the switches, which makes no sense, you can just put 0 there. Now you don't have to put 0 because in truth your hardware is not going to actually be capable of sending a value to the switches. But I think the best way to do this is just use 0. You guys with me? Right? So this is your input instruction. And then you have an output instruction for updating the hex displays, or actually it sends a message to your hex decoders, which then send a signal out to the hex displays, right? And for this, you could put 0 as the destination. See, I should be consistent. X0 and 0 are the same thing, but I should be consistent here. Let's put Yeah, let me put 0 here. I'll put x0. These need to be consistent. There we go. Yeah, so x0. Anyway, so when we want to write the values, to the hex display. I'm going to write the value in x1 in this case. It doesn't have to be x1, but whatever register you want to put out to the hex displays is my rs1, and then I'm going to specify number 2. So CSR0 is the switches, CSR2 is the hexes. Yes?
What we have immediate 12, it's not quite clear where we get it.
Yeah, that's so. I went back and forth on how to write that. So immediate 12 is that's the field in the, is it the I type? I type, yeah. The I type has a field called immediate 12, and it's the upper 12 bits. But if you look in the RISC-V specification, they don't say immediate 12 there. It says CSR, right? Which is the CSR register you have specified in the instruction, but it's the same as the immediate 12, right? It is the immediate 12. I don't know, to me it's less confusing to say immediate 12 because the immediate 12 is the way that you specify the CSR register.
So immediate 12 here, it just can be decimal number you put to say which kind of input to output you want to work with.
Exactly, yeah. And we got 12 bits even though we're only using 1 bit for this class. Okay? Now you might be thinking, wait a second, 4096 CSRs sounds like a lot, but I mean, is that the only way the CPU can communicate with peripherals? What if you have more than that? Well, actually, no. Most peripherals in practice, you're actually going to use memory mapped I/O. So you'll actually be doing load and store instructions to special I/O address ranges, right? The CSRs, I think, I don't know exactly what those are supposed to be, actually. I think they're designed for, like, on-chip peripherals. You guys with me? Like if you have a timer or, I don't know, some kind of I/O, something on chip. But like if you want to print something to your printer or you want to read a key from your keyboard, you're probably going to use a load and store instruction for that. You guys with me? But it doesn't relate to what we're doing, so hopefully I don't want to confuse you. Okay, so yeah, so the top level design, we'll have an instruction memory, the CPU, and the 7-segment decoders will be on the FPGA. And so, it's pretty simple. Pretty much just switches in and hex displays out, really. It's just one input and one output. And then, of course, you've got your clock 50 and key 0. Key 0 is our reset. And then we'll have an instruction memory. Now, we're not putting in branch and jump instructions in our code. So what's going to happen is your program is going to run, and then eventually the program counter will roll back to 0 like an odometer. And when it does that, it'll start executing your program again. So whatever program you put in this instruction memory will be running in an infinite loop because you'll run all the instructions, you'll get to the end, and then you'll reset, right? Now you might say, well, what if I don't fill the RAM? Well, that's okay, because anything you don't fill will be zeros, and 0 is a no-op. You might say, well, you didn't tell us to do no-op. It wasn't on your list. Well, yeah, because a no-op is actually a pseudo instruction that maps to something that's innocuous, it's something that writes to register 0. And that's a third usage of register 0, come to think of it, is the no-op instruction. Writes to register 0, which causes no damage. So there we go. So I came up with, there are three reasons why register 0 is always 0. Okay, okay, so we're going to be doing a three-stage CPU. Fetch, decode, execute, and memory in the second cycle. We're not really doing memory though, so you can ignore that. We used to have a data memory, but I couldn't come up with a good way to use it. Because the data memory only becomes useful if you start having data structures in the stack and a heap, right? And that would require a lot of software, right? So I don't want you guys to have to write a lot of software. So it was really hard to come up with a program that meaningfully used the data memory. So we just got rid of it. But it's not hard to add. You can see that the load and store instructions are just I type, so you could add those easily. At least the load word, store word. If you start doing load byte and store byte, then it becomes more complicated because you've got to worry about alignment and subword rights and that kind of stuff. But anyway, now why do we do a three-stage pipeline? Well, we wanted to give the fetch a whole cycle. And we wanted to give the execute and decode a whole cycle. And we wanted to give the write back a whole cycle. But that's okay because you can have 3 instructions in the pipeline at one time, and you're executing 1 instruction per cycle. 1 instruction comes off the pipeline per cycle. So that's 1 instruction per cycle. It's a little challenging though because if you look at any cycle, you got 3 different instructions in there. So when you start looking at your signals, you're like, which signal is associated with which instruction? There's 3 instructions being executed. So that's why we recommend using the naming of the signals to figure that out. Okay. And by the way, this pipelining doesn't really become complicated at all until we start doing branches and jumps. Branches and jumps add a level of complexity because you're trying to resolve a branch, but you've already got another instruction in there that you might not have wanted to fetch, but it's too late because by the time I realized it was a branch, I already brought the next instruction in. But we'll talk about that. That'll be in the next lab. Okay, so how do we design the CPU? So we're giving you the register file and we're giving you the ALU, and I pretty much, I think, give you most of the instruction memory code. So we're giving you a lot of code, but even then, a lot of students in this class don't know, like they're confused, like where do I start? Like well, it's hard to get started on this project. You basically start with the top, top down. You start with the module CPU, and you start putting stuff into it. But it is a little tricky to get started because it's a little overwhelming. But we try to give you as much information as we can. So in this case, I'm going to show the design in block diagrams, and I have I think 3 slides worth of block diagrams that convey the entirety of the CPU design. So the first thing you've got in there is an instruction memory. Now you might ask, by the way, are these blocks meant to represent modules? Not necessarily. Maybe, if you want them to. But we don't care how you decompose your design into a hierarchy. It's up to you. I personally designed the whole CPU really basically in one module, although the register file was a separate module and the ALU is a separate module. But I think everything else I just put in one big module. That's probably not the best way to do it. It's probably better to add some hierarchy. The problem with adding hierarchy, though, is for every module you instance, you have to connect all your signals into it, right? And then you end up with different signals at different levels of the hierarchy. So it does become cumbersome to add a module when you have a lot of things coming in and out because there's a lot of wiring you have to do, essentially. So just keep that in mind. But this is meant to be, these designs are meant to be conceptual. These are not, I'm not trying to imply that you need to have a control unit module. Although if Charles were here, he would highly recommend that you do that. But you could incorporate this as just an always block inside of one module, right? Okay, and then likewise, you might want to have an instruction fetch module that includes all of this stuff. The instruction memory, the program counter, and the program counter incrementer. You might want to have a fetch unit for that. So that's up to you. You have to decide how you want to organize these designs. Yes?
When I took this course, I remember finding out pretty quickly that the control unit and everything related to instruction handling was complex enough that just the if-else chain was like several hundred lines. So for me, splitting it out into a separate unit, separate file, made a lot of sense. But for you guys, it's up to you. As Dr. Bacos said, this is Verilog. You can literally stick it all in one gigantic file if that's your inclination. Like it'll compile the same at the end of the day. But you may find that debugging is easier or harder depending on where you choose to split the boundaries between the different parts. I would encourage you to at least consider it for your control unit. Maybe not so much for the fetching part, but definitely for how you break down instructions. That could be nice. At least once you get up to having dozens of instructions.
Yeah, the control unit is the biggest, is the most complex thing, like Philip mentioned. It's a big, giant if-then-else. You could make it a module, you can make it an inline if-then-else, you could even make it a Verilog function, or you could make it a Verilog macro if you wanted to. There's lots of ways you can do it. Like a macro would be like doing a define statement, like in C. And Verilog also has functions, that you could use, but we're not going to cover those. I recommend you just do it as a module or just an always statement. Okay, but anyway, so these are meant to show the relationship. So the idea is that the instruction memory, you're going to have a program counter. You're going to start. In fact, that's probably a good place to start. Program counter, right? The program counter, when you reset, it gets reset to 0, and then when you release the reset, it just, in this case, is just going to count. And there's no branch or jump instructions, so it's just literally going to count without ever stopping. It's just going to be a counter. It's going to increment once a cycle. That thing will be tied into the instruction memory. So while that's incrementing, it's going to be fetching the instruction at the current value of the PC, right? And so then you'll get a stream of instructions coming out. So when you're debugging your CPU, the first thing you want to look at is program counter. Oh, actually, clock. It's a good place to start. Do we have a clock? It's like a pulse, right? Clock, good. Program counter, is that incrementing? Okay, good. Then you look at the instruction out. Do you see a sequence of instructions being spit out, like a fire hose of instructions? So those are usually the first 3 things I check. Yes?
So basically what you're doing, you just feed in the value of program counter into the memory array of the instruction memory?
Yes. Yep, yeah, it's just, so in this case, you're just spitting out your program. And because there's no branches or jumps, the dynamic order of the instructions is the same as the static order of the instructions that you actually wrote in RARs. So, yeah, so you should just see your program coming out, basically. Okay, and then, now here's the problem with, this is the one thing that's kind of annoying about RISC. The instruction formatting is more complex than MIPS. So we've got, as I mentioned, opcode, func7, func3, the CSR field, which is also called the immediate 12 field, as I mentioned. Then there's the RS1, RS2. I don't even have these memorized yet. I used to know, like MIPS, I had everything memorized, like all the instruction formats. Here, I have to look it up. I don't remember 19 down to 15 is RS1. Like, I always have to look that up. But basically, you're going to take the instruction and break it out into fields, right? Now, there's a couple of ways you can do this. The way I did it, and again, because I usually take like a quick and dirty approach when I design these, I just took like the instruction _EX, which is the signal that's the name of the signal, and I just broke out, like I just sliced out bits for various purposes. Now, Charles came up with a better way to do this, and I think it is, and this is described in the lab sheet. I think this is a better way to do it. I think it'll save you some sanity. He proposes creating a thing called an instruction decoder, which basically just renames. It doesn't have any logic in it, but it has code in it, and it renames all the fields. It gives all those fields a name. Like, so you start out with instruction _EX, which is 32 bits, but then you can break it out into opcode EX, func3 EX, func7 EX. So that way you have this namespace of symbolic field names. Yes?
Maybe you can just define some constant and constants with the bit fields and then just end in the constants with...
You could do that too. Yeah, you could have a define in there. Verilog has defines just like in C, so you could do it that way too. So you could say like instruction EX, open bracket, func7, and then close bracket, and then that'll resolve to func7. Yeah, it's up to you. Again, this is not required. But if you read through the lab sheet, he talks about how to do that. But either way, those bits are then going to go into the control unit, and the control unit is going to take the bits from the instruction and break it out into control signals for your CPU. And like I mentioned, the control unit is just a big if-then-else statement. And I'll show an example there in a minute. Then you've got your register file, which is pretty much just hardwired directly into the instruction. So this is RS1, RS2EX, assuming, of course, that you have the decoder. If you don't have the decoder, then you would plug in instruction EX 19 down to 15 into the read address 1, because that's RS1. Instruction 24 down to 20 into read address 2, because that's RS2. And then write address. Now this one is a little bit weird, because The write address is the RD field. It's bits 11 down to 7. So you would think, oh, just plug that in like I did these two. But there is a catch here. Because the write address is something that we use for the instruction that's in the write back stage, you have to add a register there to delay. So you'll have, so you can still have an RD underscore EX, which is the RD field for the instruction that's in the execute stage, but the signal that you plug into the register file has to be RD underscore WB. Sorry, this is actually, so RDEX and RDWB. RDWB is lagging behind RDEX by 1 cycle because there's a delay element, a register, right? And the value that you actually use is RDWB because you don't want to write, you want to write back the instruction in the cycle after you execute it. Okay? So there's just a plop a register in there and add a delay. That's a pipeline register. That's all you got to do. Okay, so now I'm going to take a break from the design and talk a little bit about how you get your code in. So this is pretty cool. I'm always we've been doing this for a long time, but I'm always excited about this concept. So if you open RARS and you write your code, like you guys already did for Lab 1, you could debug your code and make sure it works, right? And that's important to do because otherwise, when you're trying to design your CPU and your software and hardware together, and there's a bug, you don't know if it's a hardware bug or a software bug. So it's good to make your software bulletproof, right? Test it in RARS. But then in RARS, you can dump the program out to a hex file, a set of hexadecimal instructions, machine code instructions, that just coincidentally happens to match the format required by the $read mem-h Verilog function that allows you to initialize a memory. That's just a nice little coincidence. The fact that RARS just happens to write to a format that can be immediately read in to initialize, read in Verilog, either for ModelSim or Quartus, that will suck in the program that was assembled by RARS into your hardware. Yes?
What if it's not a coincidence though? What if the same guys who designed System Verilog also worked on RISC-V as well, so that's why there's a compatibility between them?
It's possible. There's actually more than one. They support more than one dump format. But yeah, I think you could be right. They might have had it in mind. But also, the other thing though is it's a very simple format. It's just literally a bunch of hex values separated by white space, right? So yeah, that's the other thing. But there's other options. There's more complex formats that you can dump. But if you specify hexadecimal text, it'll just literally give you a sequence of hex values, 1 on each line. But I still like it. I think it's cool that you can write your code in, because like otherwise, think about it, like you guys would have to convert your assembly code to machine code by hand otherwise. That would really stink, right? But this way you're using Mars to do the conversion into machine code, and then you can leave Mars open when you're like debugging your CPU, and you can actually step through in Mars and compare that to what's going on in ModelSim, so you can run them side by side, which I think is pretty cool. Yes?
RARS is separate executable?
Yeah, RARS is actually a Java. It's an open source Java app, whereas Quartus is Quartus is a commercial package that we license from Mentor, or Siemens now, I guess. They bought Mentor. I have never, there is an open source actually. We used one called, there's one called Icarus Verilog that's in Linux. And so we've used that one, and there's one called Verilator, which actually converts your Verilog program and it bundles it into a simulation. It incorporates the simulation engine into your code and then makes it a standalone executable in C. And we've used that too. And it's fairly popular, but I don't like it because it doesn't support 4-state logic. So you only get 1 or 0, you don't get X or undefined. That's in Verilator. But in Icarus Verilog, that one does support 4-state logic, but it doesn't support, I think it didn't support System Verilog, or it doesn't have the latest. And all of those guys, those open source ones, have a really crummy waveform viewer called, I forget what it's called, a GTK wave that but it's much harder to use in my opinion than models. Anyway, but you can do all this open source if you had to. We've used them. But anyway, so we've got the RARs, and so you just export it as something called, in this case I called it hexcode.txt. The extension can be DAT or whatever. It's just a text file. And you put that in your initial statement there, and then your instruction mem is a memory. And remember that Verilog swaps the depth and the height, so the depth and the width. So the width is 32 bits and the depth is 4096. So this is a 4K deep by 32-bit wide, right? So it's going to be in total it's 16 kilobyte memory that you're allocating here with this one line of code, and then this line initializes it. This is going to happen when you program the FPGA. So the downside of this approach is that if you want to change your code, like say you deploy this on the FPGA and you want to change your code, you're out of luck. You're going to have to resynthesize it. There is a way you can initialize a RAM on a live FPGA using a tool called the in-system memory content editor. But when we introduced that, we used to cover that and no one used it. Because like the students felt that it was so complex that it was easier just to recompile. So we just have it, you just recompile if you want to change your software. And that doesn't happen very often anyway in this class. Okay, so then let's see. Okay, so this part is a little weird. So the problem is that the fetch takes a cycle, as I mentioned, right? So what is your execute stage going to be doing the first cycle when you power it up? Because the fetch is going to be trying to get the first instruction, and in parallel to that, your execute stage is like, it's going to be getting like garbage or something, right, from the fetch stage, right? So that first cycle is a little dicey. The way that we generally solve that is we put this reset in here. We say if reset, then we just set the instruction to zeros. It's a little hacky, but we basically put like a bypass in here, kind of like we did with the register file. And then also, if there's a reset, we reset the PC fetch. That should be indented, sorry. I don't know why it's not indented. There we go.
Thankfully, it's not a Python.
Yeah, I know. You can tell I'm not a Python guy. And then else, if you're not resetting, then you'll put instruction EX out. I think the way this works, though, is I can't remember exactly. I think when you're resetting, oh, it's synchronous, though, right? Yeah. So I don't remember exactly how it starts out right at the beginning, but this does work. So, but anyway, when you start out, yeah, you reset the PC fetch, and then when you're not resetting under steady state, instruction EX is going to be instruction mem of PC fetch. So this is your read port, and then PC fetch gets incremented once per cycle. So if any of you have any issues with the reset phase, let us know. But I think I can't remember exactly how the beginning works out. It may be that instruction EX is actually undefined at the very beginning, in the very first, right after you reset. But I guess it didn't cause an issue. I don't remember. My memory's hazy on that. But this generally works. This is essentially all your fetch logic here. Okay.
In the first cycle, can you just go through?
Sure. Go back.
Well, actually, when we have instruction memory of PC fetch, and PC fetch is 0 from after reset, you just got 0 and instruction execution. And I think it's no op or something like this.
Yeah, I think when you synthesize on the FPGA, the instruction EX, being that it's a register, gets reset to 0. And so I think what will happen on the FPGA is when you bring it up, you'll probably end up with the first instruction on instruction EX. But in model sim, it'll probably come up as undefined at the beginning, right? So I think that might be what it is. We probably should fix this up a bit and make it a little bit more clear what's going on at the beginning. But like I said, this is something you can, I think in general, everyone just uses this code and it's okay. Okay. Okay, so here's the execute and write back stages, all kind of mashed into one design because we've got the pipeline registers here, so technically there's two stages here. Okay, so we have the control unit, and now we're finally showing you now what kind of control signals we have. And there's not many of them. There's actually less than there is in MIPS. There is a reg write signal that is the write enable for the register file. Because we're using R-type instructions, I think that's always going to be 1. Because I think all the R-types write to a register, right? So generally you're going to have that as a 1. Reg Select gets delayed by 1 cycle and becomes Reg Select EX becomes Reg Select WB, and it goes into this MUX. This MUX is important because it controls what gets written back to the register file. In this design, we have 3 options. And this might not be the best way to do it. There's probably a more elegant way to handle this. Actually, it's a little hacky, but basically, the first option, which is actually tied to input 2 on this MUX, is just the output of the ALU delayed, right? And that's most of the time that's what you're going to be using. You're going to take whatever the ALU calculated and you're going to be writing it back, right? But what about if you have a load upper immediate instruction? The question is, can you get the immediate and route it through the ALU, or do you have to create a totally separate special case for the load upper immediate? Well, the problem is that RISC kind of screws this up, because in the old days of MIPS, the immediate field was always 16 bits. So I used to do a trick where if I did a load upper immediate, I would just take the immediate and shift it 16 bits to the left and then write the result back. That way I could route the load upper immediates through the ALU. But the problem is that RISC-V has a 12-bit immediate field and a 20-bit immediate field. And so if you were to try to do that with RISC, you'd have to have a MUX here to control. You'd have to be able to select A as the 20-bit immediate and then shift that by 12 bits. So I don't think that would be any better. So this might be the best way to do it. But anyway, the point is that if you do a load upper immediate, you set this MUX to 1. And then you have a little custom shifter that takes instruction EX bits 31 down to 12, which is the leftmost 20 bits, shifts it 12 bits to the left, and routes that and just shoves that right down the throat of the register file through that path. All right, using input 1. So Reg Select would be a 1 for a load upper immediate, and it would be a 2 for just about everything else, except for the CSR instruction, which is in that instruction we want to be able to take the switches, the switch input, and we need to get that into the register file. That way otherwise your program won't have any way to get input from a human, right? So for that, we have input 0, which is basically just the GPIO in. Right? Now you might say, why do you need a register for that? Like, do you honestly think like someone's gonna be switching the switches so fast that you might be off of 1 cycle timing on that? No, it's probably a little gratuitous to have a register there, but I just put it in because we register all the inputs to that MUX. Yes?
Why we have all these registers for cycle delay?
Why?
Yeah.
Oh, just because the write back stage. The write back stage happens in the cycle after. So basically what the way the stages work is the fetch stage is nothing more than the program counter reading an instruction. That's it. Now once we get to branches and jumps, we add a little bit to that. But in this lab, it's pretty much just reading a synchronous instruction memory. That's all fetch is. And the only signal that has the fetch suffix is the program counter. Program counter fetch, PC fetch. So there's very little going on in fetch. Then in the execute is where most of the action happens. That's where our instructions are decoded from the register file, and that's where the control unit takes the instruction and converts it into microcode, or control signals, right? Then the write back stage is all of the stuff needed to write a register back. Now unfortunately for us, there's quite a few of those because reg write is a write back stage, right? Reg Select is a write back stage, and all the data that we want to write back is in the write back stage. So you have to add, that's what all these registers are for. It's basically just to make sure that when you write back, you're writing back the instruction that was fetched 2 cycles ago, while at the same time you're executing the instruction that was fetched 1 cycle ago. Right, so this is the reason why on that quiz I asked so many questions about, the delays and the registered logic.
Wouldn't it be better to put the register before writing to the reg file, but after the selector? So we input and select
Yeah.
have, but delay.
Yeah, you mean put it here?
Yeah.
Yeah, you could do that. In fact, that's a good point. I think the reason we didn't do that here was because of a historical reason. We used to do memory, as I mentioned. We used to have load instructions, and when we did the load instruction was asynchronous. So, whenever you'd load an element from memory, a word from memory, that would push it into the next stage. So we couldn't do it that way. But now because we don't have the data memory, we don't have load instructions, then actually you're right. You could alternatively just put a register here. That would eliminate those 3, but you'd still have to have these 2, right? So there is different ways you could arrange that. So I think I left it that way just because we thought maybe we might want to put the data memory back in. But great question though. Okay, and I think this is the last slide. So this is the I types. Yes, sorry. So everything I've showed you so far was R type. You have to do a couple changes to support I type instructions. Actually, this is the only thing you need for the U type. Is this little line of code there in this, where's it go? This second input on this mux. So I've already showed you all the R-type stuff and all of the U-type stuff. Now I-type pretty much just requires one extra thing, a mux on the ALU. You have to be able to mux and select between the contents of the RS2 register, the second operand, register operand, or the sign extended immediate 12 from the instruction. That's it. That's really nice. Now with MIPS, I don't know if you guys probably don't remember this from 212 because it's been a while, and this is kind of a subtle detail. But in MIPS, you had to add a mux here for the register file destination because there was different destination fields, whereas now we just have one RD field, which is universal. That's nice. And MIPS had a 0 extend option as well. So in MIPS, if you did a logical immediate, like an AND I or an OR I, you had to 0 extend it. But RISC-V got rid of that. RISC-V says you sign extend everything. So you have to be careful when you use like an OR I instruction because the immediate's going to be sign extended. You may not intend for that in your code, but that's something that that simplifies the hardware at the cost of possibly complicating your software a little bit. You guys with me? Just to clarify what I mean by that, when you do a logical operation like or AND, there is no sign bit. The sign bit there's no concept of a sign bit unless you're doing an add or a subtract, right? Or a multiply or divide, right? But if I'm doing an AND I, like I'm doing a logical, bitwise logical, what's the significance of the sign bit? Nothing, right? So we shouldn't be sign extending a logical immediate instruction, but again, by forcing all of the immediates to be sign extended, it makes this simpler. So it makes it easier, for the hardware. Hardware is simpler. This mux ends up just being 2 inputs instead of 3. Okay. All right. So how do we actually build the control unit now? This is the hardest part of the lab, but it's really not that bad if you understand how these data paths are being constructed. So how do you build a data path? How do you route data through your CPU? Well, essentially, it's just mux selects, really. It's just you got some muxes, you set the selects. And by setting the mux selects, you can steer data around internally, right? You can reconfigure the paths the data take. And then, of course, there's a couple extra things like the reg write and the GPIO write, which just controls the register that writes to the hex display. So I didn't talk about that yet, but basically, the hex displays are assumed to be driven by a register, meaning that if you don't have a software instruction to update the hex displays, you don't want them to change, right? Otherwise, you won't be able to note it. As a human being, you want those hex displays to persist until they're supposed to be updated. Otherwise, they're going to get cleared after one cycle. You only have your hex value there for a 50 millionth of a second, right? So anyway, so you have a GPIO write enable that will simply update the hex displays, right? So there's 2 enables, and then I think these 2 are mux selects, so these are only 2 muxes here. ALU source and Reg Select. Again, Reg Select is what we're writing back. There's 3 options there. ALU source is whether you're taking the register or an immediate in the ALU. And the ALU op is from your ALU op code, your list of ALU ops, which are here. Okay, so let's fill this in. So if you're doing an add instruction, actually, I filled this in by column. So here's the instructions I've got so far. Add, subtract, multiply, and set less than. These are all R types. They're all very similar. Basically, the only difference is what ALU op code you use, right? So ALU op is pretty much, you just have to do a cross-reference to this table. So you cross-reference this to that. So basically add, you look up add, which is 0011. Subtract, that's 0100. Multiply, 0101. So you just look it up, right? ALU source, because these are R types, you don't want an immediate going to ALU, you want the both registers, right? So ALU source is pretty much always going to be a 0 here, right? Because I just want to take the RS2 register, that's always 0. Reg Select, same thing here. The Reg Select controls this mux, and I always want to take the output of the ALU. So Reg Select should always be 2, right, for all these guys. So I'll just fill in 2, 1, 0. Reg Write, well, that just controls whether you write the register. All these guys write the register, right? They all output their result to the register file, so that should always be 1. And GPIO write enable, well, I don't want to, none of these are IO instructions, so that should all be 0 as well, right? Make sense? Yes?
Excuse me, can you please tell one more time why we have ones for Reg Write?
I'm sorry, what was that?
Why we have Reg Write ones?
Reg Write 1?
Yeah, 1, 1, 1, 1.
Oh, it's 1 because, so the register file has that write enable. And so some instructions, but very few, don't write a register. For example, store word, which we're not even going to do. One of the GPU, actually the IO registers write a register too. I think everything writes a register, right? Except for the jump and branch and jump instructions, which we're not doing. So I think in this lab it's always going to be 1. So it seems a little redundant, but once we get to the branch and jump instructions, then it will become important. Oh, yes, also if you're stalling, eventually we're going to have a stall instruction, which is going to be used for branch and jumps, like a bubble in the pipeline, like a no-op, and we're not going to want to write the register then. But for now, it's always 1. So yeah, you're right, it's a little redundant. Okay, and I, SLL, SLLI. Okay, ALU op, again, is just a cross-reference to those specific operations. ALU source, now here, ALU source is going to depend on if you're doing an R type or an I type. So ALU source is a 0 for the and the SLL, but it's a 1 for the and I and SLLI, right? Because those are I type instructions, so their second operand comes from the immediate. Reg Select is, I think, just always 2 again. Reg Write's always 1. GPIO write enable is always 0, so those are always the same. Okay, how about load up or immediate? Okay, this one is a little different. Load up or immediate, I don't care what the ALU op is, because as I mentioned, the load up or immediate uses this mux to bypass the ALU entirely. So you can just put X for that. You can actually put X into Verilog and it'll treat it as a don't care. Or you might just want to set it to 0, 0, 0, 0. CSRRW, yeah, same thing. I don't care what the ALU op is for that either. Those are I/O instructions. They don't use the ALU. ALU source, also don't care. Not using ALU, don't care what the ALU source is. ALU can take whatever it wants, whatever happens to go in its second input. Reg Select. Reg Select is, okay, so this part, Reg Select is a 0-1 for the load up immediate, because that's our special path specifically for that. Right? Now, this is a little weird. The CSR, so the way I have this written is I split it out into two. So there's one CSR instruction, but I split it into two rows. One for the hex, one for the switches. These rows are differentiated by immediate 12. Now, as I mentioned, do you really have to do that? Because probably don't have to do that. We did it just to make sure that you don't write to a register if you are writing the hex values. That's the only reason we did that. It may not be, I don't think it's entirely necessary, but I broke them out into two separate. And then Func3, oh sorry, yeah, the Func3, oh by the way, I didn't mention this earlier, but the Func3 and the opcode, you have to look these up. These are all obviously unique to each instruction. Each instruction has its own, you know, Func3, Func7, and opcode, right? That's how you differentiate. Because like notice how I have a column for instruction, but you're not going to have a column in your control unit. Your control unit is going to know what instruction it is based on these bits, right? Right? Okay. Reg write. So notice how reg write I put as a 0 if you're reading, I'm sorry, if you're writing the hex. Right? So that was, I think that was the main reason I have two rows for that. Those two variants of the CSR instruction. And then the GPIO is going to be one only for writing the hex. Okay? So this is the whole table. This is not complete, obviously. There's 22 total instructions, and I'm only showing 2, 4, 6, 8, 10. This is 10 of the 22. So we're giving you most of the information you need for the control for 10 of the 22 instructions. You're going to have to fill in the rest, but most of them are, I mean, as you might imagine, they're all just slight variations. The other ones are slight variations on these ones. Okay? Okay, and then we're going to give you, this is a test program that we provide to make it easier for you to test your CPU. So you can copy and paste this into RARs, generate the corresponding machine code, run it through your CPU, and this will execute one copy of every one example of every instruction. And in the comments, we actually show you what to expect to be written in the register file for each instruction. So this is a nice little test bench. In addition to writing this, you're also going to write another program that's actually going to make the board do something practical, which is going to be the converting the binary switch value to a decimal base 10, binary to base 10 converter, which I'll talk about next week. Yes?
Why you have this division mark, like register, for example, first line, X1 will be set to 12 or?
Yeah, I'm showing the decimal and the hexadecimal because the reason for that is because in Model Sim you can have them displayed in hexadecimal or decimal. Same thing in RARs. RARs allows that. But some of these are arithmetic, like where you're doing something that's obviously arithmetic, like -8, right? But -8 makes a lot more sense to me than FF, 8, right? So I show both just so you can use either representation. But that's not a divide. That's two different bases. Okay? One other thing I want to mention is if you get started early, RARs does not understand these RARs understands the CSSR instruction, but it doesn't know that, wait, why are we using, oh yeah, F2 and F0. Philip, do you remember why we're using why is it FO2 and FOO for the CSRs in here? Do you remember why we did it that way?
Because you had to pick a particular register value for the CSRs. I feel like that was just the code that Charles made. identifier for those slots to correspond to different things externally.
Okay.
I don't think there was too much conscious choice in it. He might have picked them to start with F on the left there, specifically to avoid any of the traditionally used ranges.
Okay. Yeah, so just be aware of that. Also, notice that this format, this assembly language format's weird because normally whenever you have an immediate, it goes last.
Yeah.
But this one has the destination first, the CSR register second, and then the source, RS1, comes third. So this is a bizarre, in terms of assembly language, this is unique, right? It bucks the convention a little bit. So these ones are, I mean, even these still confuse me looking at this formatting here. Just be aware of that. But that's the way, where we're going to get data in and out. Okay, great. We'll see you in lab this week.